Hi, so finally we'll bring everything together from the previous videos and prove the option pricing formula for this Black-Scholes model of a simple kind. So I start with assuming that we have a predictable strategy. ANVN is a predictable strategy. And of course, in real life, all strategies are predictable because we don't see into the future. And I define the discounted value of our wells, yn, as 1 plus r to the minus n times xn. Okay, 1 plus r to the minus n times xn. This is the discounted value of our wells. So remember that our total wells we have on day n is an many stocks and vn many bonds, or we can do some exchange by the end of the day. It's an plus 1 many stocks, vn plus 1 many bonds. That's the total value of our wells. The fixed interest rate for bonds is r, so bonds go up by a factor of 1 plus r every day. And if I discount back by 1 plus r to the minus n, that's the present value on day 0 of the wells on day n. Okay, now what we're gonna do here first is define the probability in the appropriate way so that this quantity here is made into a martingale under any predictable strategy. That's the first step to do. Okay, so how do we do that? So I'm going to first write xn in a few different forms. I start off with the previous observation we had, that xn is ansn plus vnbn. So let me write that out first. 1 plus r to the minus n and ansn plus vnbn. Okay, and from here I'm going to do 1 plus r to the minus n times ansn for the first bit. I'm not changing that. But then 1 plus r to the minus n times bn. 1 times r to the minus n times bn is just b naught. So this bit here, bn times 1 plus r to the minus n, is simply b naught. So I'm going to write that first. And that tells me that I have the vn, and then 1 plus r to the minus n bn, that's b naught. So that's one way of writing it. And I'm going to write it in another way too. I'm going to use the end of the day formula for my total wells. The end of the day formula is that instead of a and vn, I do some exchanges, and it's an plus n, vn plus n by the end of the day for stocks and bonds. And I'm going to put that in. So it's going to be an plus 1 of stocks and vn plus 1 of bonds. And then when I factor out 1 plus r to the minus n, I'm going to keep that on the a's, but again I'm going to write 1 plus r to the minus n bn as b naught, so I can have vn plus 1 of the b naught. So that's another way of writing it. Okay, so it's a bit of algebra at this point. Now if I do yn minus 1, and I'm going to use the first line, 1 plus r minus n, 1 plus r to the minus n, ansn plus vn b naught. I'm doing the first line for yn, but I'm going to do the second line for yn minus 1. So I'm going to copy the second line here, except that I have to use n minus 1 for n. So it's going to be 1 plus r to the negative n minus 1. So that gives me an n plus 1 here. A of n, Sn minus 1 plus Vn of B naught, and all of that is with a negative. Okay, so what I did here is plugged in yn minus 1 from the second line with a one less index. So instead of n, I have n minus 1s everywhere. Okay, and now cancel out whatever we can. So the Vn B naught cancels. The an can be factored out, and so it actually becomes quite nice. The 1 plus r to the minus n also factors out. So 1 plus r to the minus n, an, those factor out. And then what is left is what? Let's see. So I have an Sn here, and I have an extra 1 plus r and Sn minus 1. 1 plus r and Sn minus 1. Okay, which is just equal to 1 plus r to the minus n, 1 plus r to the minus n, and then 1 plus r to the minus n, and an, and just simplify. Oh, okay, and then okay, there is one more step I want to do. Sorry, there's one more step I want to do, and that's the following. I want to plug in Sn from here. This is from a previous video. Sn is the random rate multiplied by 1 plus the random rate multiplied by Sn minus 1. So this is going to be the random rate 1 plus Rn. This is how I get Sn from Sn minus 1, just considering the random rate from Sn minus 1, and I still have 1 plus R Sn minus 1 here at the rear, and so I end up with 1 plus R to the minus n, an, and then I can do the difference here. So there's the random rate Rn minus R times Sn minus 1. So that's a useful formula. Okay, so that was the first thing I wanted to do here. And the next step is that I'm going to write in the random rate. So I'm going to assume now, next I'm going to assume that P, let's fix P at R minus A over B minus A. Notice that at this moment I just have some predictable strategy. I didn't yet really have a probability space, right? I just have a predictable strategy. It just tells me what to do if I see certain happenings in the stock market. I didn't really have anything random at this moment. I just have some happening in time. And now I want to put a probability space behind it by fixing this p-value. And first I do some calculations on this with this p-value. Let's solve it for r first. So what is r? R is going to be, if I cross multiply, it's going to be b minus a times p. So far it's r minus a, so if I add a, then this is what r is. And there is a nice way of rewriting that, and that's a plus b over 2 plus b minus a over 2 times 2p minus 1. Okay, why is that? Because, okay, you just check. B minus a times p is here, b minus a over 2 times 2p, that's there. And if you add a plus b over 2 with a minus b over 2, that gives you b minus a. Is that right? No, sorry, that gives you a, of course. So a plus b over 2 plus a minus b over 2 gives you a. So these two are just equal. And if I now look at this formula from before of the random rate, so the random rate Rn is a plus b over 2 plus b minus a over 2 times omega n, and the mean of omega n according to that probability because omega is plus 1 minus 1 with probability p1 minus p. With that probability, it's actually just the mean of the omega n. So if you compare the random rate, a plus b over 2 plus b minus a over 2 omega n, if you take an expectation of that random rate, you get exactly this non-random rate, a plus b over 2, b minus a over 2, 2p minus 1. That's what fixing p at r minus a over b minus a exactly does. Okay? It just makes the random rate average to be the non-random rate. Okay, and if we have that, then the next thing I want to do is plug that in the formula for yn minus yn minus 1. So 1 plus r to the minus n, an, and then rn minus r. If I look at rn this way and r that way, and I make the difference, then the a plus b over 2 will go, and the b minus a minus 2 will survive with a factor of omega n minus 2p plus 1. So that's what I'm going to put in now. It's going to be b minus a over 2 with a factor of rn had omega n in it, and r has 2p minus 1 in it. So I arrive to this formula here. Okay, and now I'm going to do something kind of nice, or if you want strange. I'm going to now find a predictable process hk. I'm going to define this thing here as hn. I'm going to define, and you don't see that, so I'm going to define that part as hn. Okay, so this is hn, and notice that, oops, I forgot the Sn minus 1. I forgot the Sn minus 1, so let's put that in here. Sn minus 1, and that's part of my definition for hn. Okay, so hn is this discounting factor, is the an, the strategy an, Sn minus 1. Notice that everything here is Fn minus 1 measurable. The an is a predictable strategy, so it's Fn minus 1 measurable. Sn is of course n minus 1 measurable. So this hn is n minus 1 measurable. So this is predictable. Okay, this is predictable. And if I go back to, well, first of all, if I just repeat what I have. So this is hn times omega n minus 2p plus 1, hn times omega n minus 2p plus 1. If I now go back to part of the proof of the lemma, which said that if I have a Martingale transform of z, then the increment of my Martingale is exactly hn times omega n minus 2p plus 1. That exactly means that y is a Martingale transform. Just looking at this line backwards, it exactly means that y is a Martingale transform of that z basic Martingale with h. So that exactly means that y is a Martingale transform of my basic Martingale with this h. Okay, so that what we conclude from here is that yn, the discounted value of my wealth, is actually y naught plus the Martingale transform of that elementary Martingale z by h. Okay. Now what can we? So that's the starting point. That's the basic starting point for proving the Black-Scholes formula, at least in this simple model. Okay. So what does that mean? What can we read of that? The first observation that I want to make is that y is a Martingale. So for any predictable process, we managed to find a Martingale as the discounted wealth of the discounted wealth we have is going to be a martingale according to this probability space here. If we pick P this way, then the discounted wealth we have is going to be a martingale. Okay? So it follows that Yn is a martingale. By picking that particular P. So remember that we picked P equals to R minus A over B minus A, which is a probability by the assumptions on A, B, and R. Okay, so Y is a martingale. Okay, what is X naught? So suppose that we have a hedging strategy which starts with X, right? So we assuming that we have some kind of a hedging strategy, it starts with X. Okay, just by definition of a hedging strategy, that's the value of the hedging. Okay, let me just bring back the theorem we're actually proving. So we're looking at hedging strategies for the European option, and that satisfies these properties. So it's a hedging strategy with initial value X, and so what we're doing now is we assume that we have such a hedging strategy, and we want to show that the value X has to be, we're proving this theorem, so we want to show that the value of the hedging strategy, the initial value of the hedging strategy, has to be exactly this thing here. Okay, and so assume that we have a hedging strategy, so that comes with some initial value X. What is the connection to X naught and Y naught? Well, Y naught, according to our definition of Y naught is 1 plus R to the 0 X0, so it's just X0. So Y naught is the same as X0. Now, Y is a martingale, so because it's a martingale, I can write it as Y naught is, it's not random, right? It's a fixed initial value, so it's not random, but it's not changing in mean. So the expectation of Yn is the same as the expectation of Y naught. What is Yn? Yn is Xn discounted back. Xn discounted back by the bond rates. So that was the definition of Yn. And now if I want a hedging strategy of the European option, that means that Xn has to be the value of the European option at time n, because that's what I want to hedge. So that's going to be Sn minus k positive part at time n, because the hedging strategy exactly means that Xn is Sn minus k positive part. Okay, and okay, we're almost done. So let me just factor out this non-random part 1 plus R to the minus n. What's left is expectation of Sn minus k positive part, and that's exactly what the theorem says. We have a hedging strategy for the European option if that's the initial value. Okay, so that's one direction of the thing. Suppose we have hedging strategy. Suppose that it hedges the European option, so at time n it has to be Sn minus k positive part. Then its initial value is 1 plus R to the minus n expectation of Sn minus k positive part. So that proves one direction of the theorem. If there is a hedging strategy which hedges the European option, then that must be the initial value. Okay, now let me then prove the other direction. So now let's prove that if X is expectation of 1 plus R to the minus n, actually I can factor that out, 1 plus R to the minus n expectation of Sn minus k plus, then what is the hedging strategy? then show the hedging strategy. Hedging strategy. How do we show the hedging strategy? Well, it's easy, because for that direction what I'm going to do is I'm going to build up the probability space. So consider P equals to R minus A over B minus A, and the probability space we started with. So consider this plus minus ones. According to that probability space with this probability value, we can build up a martingale. Okay, we can build up a martingale, namely yn is going to be the expected value of r plus 1 to the minus n, and then Sn minus k positive part given Fn. This thing is going to be a martingale just because it's a random variable under the conditional expectation with respect to the nth term of a filtration. So this thing is a martingale. Okay, if this thing is a martingale, then use the lemma. Use lemma to find a predictable process. So where is the lemma? Here is the lemma. If you give me a martingale, then there is a predictable process H for that, so that the martingale is a martingale transform of this basic martingale Z. The predictable process has some explicit formulas, whatever that is. So start with this martingale. For that martingale, find the predictable process. Find the predictable process Hn using the lemma. Once you have Hn, then once you have Hn, then you can define via this formula, you can define your predictable hedging strategy An. Okay, so once Hn is found, you define An by this formula from the previous calculation. Okay, so then use the previous formula to find An. Okay, and with that formula, you know that you have your martingale. It tells you what the predictable strategy is. So every calculation we did here actually makes perfect sense, and we know that our wells is xn equal to 1 plus r to the n times yn. Okay, and what you want to check is that the initial value and the end value are actually correct. So check that x naught equals to 1 plus r to the 0 y naught is what we need. Well, it's exactly, so what is 1 plus r to the y naught? It's 1 plus r, or r plus 1, doesn't matter, 1 plus r to the minus n, expectation of Sn minus k positive part given f naught. However, f naught is trivial. F naught is trivial, which means that conditioning on it just gives us back the unconditional expectation. F naught is trivial, so this conditional expectation is just the unconditional expectation. So Sn minus k positive part, and that's exactly what we wanted. because we started to assume that x naught is the hedging strategy initial value, so that matches, that's fine. And also check that the terminal value, the wells at time n, works. So what is that? It's 1 plus r to the n times yn. In other words, 1 plus r to the n, and then 1 plus r to the minus n from here, times the expected value of Sn minus k positive part given f capital N. That's what Xn is, according to the strategy we found. That's what Xn is. Now notice two things. First, that you cancel out the rates because it's plus and minus n power, they cancel out. Second, that Fn makes Sn, so Sn is Fn measurable. So this conditional expectation is not there. It's simply Sn minus k positive part. Okay. So what did we find? What did we find? So we had this initial value of 1 plus r to the minus n expectation of Sn minus k plus, and for that we found we built up a probability space. We found a martingale. From that martingale we found a predictable process. From the predictable process we had a formula to find the hedging strategy AN itself, which of course implies what Vn is, so it's really the AN Vn pair from here. And then we checked that what we found actually satisfies the definition of hedging strategy. It does go from the initial value that we need. It's non-negative, that's easy to check, nothing is negative here, so homework checked it's non-negative, and the terminal value is what it needs to be. So assuming that initial value, we did find a hedging strategy that satisfies all the definition of the hedging, and it hedges the European option. So that was the second part of the theorem. So we proved that if there is a hedging strategy for the European option, then the initial value is this. That was in the first part of the proof. And for the second part of the proof, we found that if there is an initial value of expectation 1 plus r to the, where is it, this one here, if there is an initial value of 1 plus r to the minus n Sn minus k positive part expectation, then we can build up a hedging strategy for that. And we used this artificial probability space, the martingale, and the formula for the predictable process for that. And that completes the proof. I am not going to show you here the last bit of the proof of the statement. So the proof of the last bit is that AN is non-negative. So when you do all of this, then the strategy you find here is actually non-negative. I'm not going to do that here in this video. If we have time, then we're going to do that in the problem class.